In this lecture, I'm going to talk about doing calculations for standing waves. And standing waves are a combination of modules 11 and module 12. Since it occurs in both, I decided to put them together for you. So we know that when two waves interfere with each other, they add together. So if you have two waves that are completely in phase, so their peaks occur at the same point and their valleys occur at the same point, they're going to add up to give you a wave that's twice as high and with the same frequency. If they add up so that one has its peak when the other one has its valley, they both are zero at the same point, etc. If you add them together, you're always going to get zero, and we call that destructive interference. So if they're completely in phase, it's called constructive interference. You get a larger wave. If they're completely out of phase, which is 180 degrees out of phase, you'll get zero, which is called destructive interference. And usually what we get is something in between the two, and so we get a partially destructive or partially constructive interference. When waves reflect at boundaries, they get reflected back to the way that they came. If it's a hard reflection, so the string, for example, is tied down at one end, the reflected wave comes back upside down. So you can see that that could add destructively. If it's not tied down, so the end of the string is free to move up and down, the reflected wave will go back upside right, the same direction as the incoming wave. And same thing if it goes from a less dense material to a more dense material. So if you have a light rope tied to a heavy rope, you can get part of the wave is transmitted and part is reflected in an inverted sense. So this is how standing waves are set up, that the wave goes down the medium, it reaches the end of the medium, and it's reflected back and it will interfere. And if it interferes in a certain way, we get what's called standing waves. So standing waves in the string, if both ends of the string are fixed, what happens is that only waves with certain wavelengths are allowed. And there's a picture here of 3 different standing waves that are allowed. And you can see there's positions called nodes and antinodes. A node is where there's no amplitude. The amplitude's always 0. And in an antinode, the amplitude varies from 0 to the maximum value of amplitude. So here's an example of the lowest frequency standing wave, and you can see that it's got one antinode in the middle where it moves up and down, and 2 nodes where the string stays in the same position at the same time. The next allowed frequency, you have 3 nodes. You're always going to have a node at each end of the string, and here we have a node in the middle as well. We have 2 antinodes where the string goes up and down between maximum amplitude and minimum amplitude. And similarly, we go up to another level, we get an additional antinode, an additional node, and same thing again. You'll notice there's always one more node than antinodes. And we use these standing waves to create musical sounds. So musical instruments can be things like vibrating strings, so guitar or violin or cello, vibrating membranes like a drum, vibrating metal or wooden shapes. So if you play something like a xylophone, for example, or vibrating air columns, which is the case for all wind instruments. So it turns out that these frequencies for the standing waves have certain values depending on the length of the string and depending on how tight the string is, which determines the speed. So the wavelength of the string is twice the length of the string divided by n, where n is the number of the harmonic. So we can have the fundamental, and we can have the fundamental as the first harmonic. Then we have the second harmonic, which has n equals 2, the third harmonic, which has n equals 3. And the second harmonic is sometimes also called in music the first overtone, and the third harmonic is called the second overtone. So you can see that for the first one, where n equals 1, we basically just have half a wave. If I continued that on, you would have the other half of a wave. In the second harmonic, you can see that's a complete wave. In the third harmonic, you get 1.5 waves in there. So the wavelength is 2 times L over N, where N equals 1, 2, 3. So for N equals 1, the wavelength is twice the length of the string. For N equals 2, the wavelength is 2L over 2, or just the length of the string, etc. The frequency is equal to V divided by the wavelength. Remember, always V equals lambda F for a wave. Okay, so the speed of the wave, which is determined by how tight it is and what the string is made of, divided by the wavelength gives you the frequency. So the frequency is equal to N times the speed over 2L, and this V over 2L is just the fundamental frequency. So the frequency of the second harmonic is just 2 times the frequency of the fundamental frequency, and for the third harmonic it's 3 times, etc. And here's another picture showing you the waves more sort of blown up, and you can see that the frequency and the wavelength equations are given for each of those. And for each wave, you have a node at each end where the string is tied down. And each time you add, you go up to another N, you get one more node. You always have one more node than N is. So N equals 1, you have 2 nodes. N equals 2, you have 3 nodes. N equals 3, you have 4 nodes. And you have the same number of antinodes as N. So N equals 1 has 1 antinode, N equals 2 has 2 antinodes. And you should be able to know that, and you should be able to sketch a wave. So if I told you sketch the wave for N equals 3, you should be able to sketch it for me on the test. So how do we determine the wave speed? Well, the strings on a guitar, for example, when you tune it, you can change the string density, and you can change the tension on the string by turning the knobs at the end over there. So you turn the knobs to tighten or loosen the string to change the frequency. And you can also finger a guitar. So when you play a guitar, you put your fingers on, and that shortens the length of the string, and that raises the frequency that you hear. So fingering changes the length, and turning the knobs changes the tension. And the different kinds of strings on the guitar are made out of materials with different densities. So we know that the equation for waves on a string is that the wavelength is 2L over N. We know we can change the L. And for frequency, it's V over 2L times N. So the length comes in, and so does the speed. The speed for a wave on a string is the tension force divided by the mass of the string divided by its length, or we have another thing, mu, which is the mass per unit length, or it's also called the linear density of the string. So you could be given the mu value, in which case you just put it down below, or you could be given the mass and the length, and then you'd have to calculate it that way. Okay, so for example, if I said, what's the speed of a wave on a guitar string that has a mass density, which is mu of 0.004 kilograms per meter, and it's under 520 Newton tension, I'll just put in V equals the square root of the tension over mu, so 520 divided by 0.004, and I get 360 meters per second for the speed. And that seems quite fast, but remember the speed of sound in air is about 340 meters per second. So if I continue on for that same guitar string, I want to find what's the frequency and the wavelength of the fundamental and the first 2 overtones. So that means N equals 1, 2, and 3. If the string is fingered to a length of 62 centimeters, so you put your finger on there to change the length of the string to 62 centimeters. So remember, I'll bring over the speed from the previous slide. So V is equal to 360.555 meters per second. And there's my equation. So all I have to do is basically just plug and chug into the equations. So I'm going to put in for N equals 1, 2, and 3 that the wavelength is 2 times the length of the guitar string, which is 62 centimeters or 0.62 meters, divided by n. So I'll get 1.24 meters, 0.62 meters, or 0.4133 meters, or if I put it in the same units as the problem, 124 centimeters, 62 centimeters, and 41.33 centimeters. Okay, how about the frequency? Well, frequency is the speed over the wavelength. And here I have to put the wavelength into meters to match the units on the top, which are in meters per second. So if I put those in, I get that the frequencies are 290.8 Hertz, 581 Hertz, and 872.4 Hertz. I could also have done for the frequency of the second one that it's 2 times the frequency of the first one, so 2 times 290.8. And for the third one, I could have said that it's 3 times 290.8. So again, we have multiple equations. There's more than one way to solve it and get the correct answer. How about wind instruments? So when a wind instrument, you blow air in one end and the air goes through, you can change the length of the tube by your fingering over the holes. And then it comes through and either reflects at an open end, for example, on the clarinet there, you see the plane, or it could be on a closed end. So standing waves are created by reflections at the end of the pipe. If it's an open end, then you get a soft reflection. So at the end you have an antinode. So the air is moving at its maximum amount. If it's a closed end, then it's a hard reflection. You're going to have a node at the end. So if the tube is closed at both ends, then you're going to have nodes at each end. And so what you're going to get is something that's exactly the same as the waves on a string. And so the allowed frequencies and wavelengths will be exactly the same equations as we had for the waves on the string, that the wavelength is 2L over n, and the frequency is n times V over 2L. And we'll use the same thing. N is equal to 1 is the fundamental frequency, n equals 2 is the second harmonic, etc. And in this case, V is going to be determined by the speed of sound in air, which depends slightly on temperature, and it's usually on the order of somewhere between 340 and 343 meters per second. Sometimes people who play a wind instrument may have to adjust their tuning as time goes on and they've been holding their instrument for longer and it gets warmer. If the tube is open at both ends, which is the case for a lot of wind instruments, then it's got antinodes at each end. But if you look at it, if I look at the first one, you can see that that's actually also half of a wave. If I try to sketch the other half of the wave, you can see it's over here. It's not a very good job. So that's actually half a wave. If I look at the second harmonic, that's actually a whole wave. If I look at the third harmonic, that's a wave and a half. So it's the same thing as for a string. It's just that I've shifted down where my ends are so that I'm at the peak positions instead of being at the nodes. I'm at an antinode. And so it turns out that the equations are exactly the same. So it doesn't matter if it's closed at both ends or open at both ends. The equation is going to be exactly the same for the wavelength and for the frequency. If you have a tube that's closed at one end, so for example, that might be some organ pipes, then you have a node on one end and an antinode at the other end. So you have a node at the closed end, an antinode at the open end, and so that means that your first allowed frequency is actually going to be just a quarter of a wave, right? It goes from the peak down to the node, and so the wavelength is going to be 4 times the length of the tube. So the allowed wavelength is 4L over n. The next one is going to be half a wave plus another quarter of a wave, because remember I have to have a node at the closed end and an antinode. So I can fit in a quarter of a wave, 3/4 of a wave. The next one up I would have a whole wave plus a quarter of a wave. So you can see I'm doing 1/4, 3/4, 5/4, 7/4. So the allowed wavelengths are 4L over 1 over 3 over 5. I can't have any even numbers for my harmonics. And the frequency, since the frequency is V over lambda, the frequency is also going to have that 4L dependence, and the allowed values of N will be 1, 3, 5, and 7. So then I'll have to use NV over 4L to get the frequency. So remember, for a tube that's closed at both ends or open at both ends, it acts exactly like the wave in a string. It's only if it's open at one end and closed at the other end that you have to worry about using this different equation. So let's do a couple of examples using these pipe calculations. So let's say I have an organ pipe that's open at both ends, and they tell me that its second harmonic has a frequency of 523 hertz. I want to know what's the length of the pipe. Okay, well, my equations are shown there. It's the same as for a string. And the second harmonic, it has n equals 2. Okay, so if I know my n equals 2, and I know my frequency, so I know f equals 523, I know that n equals 2, and the speed of sound in air is 343 meters per second, typically at 20 degrees C. So now I can rearrange my equation to give me the length. Okay, so I've got the frequency is 2V over 2L. So the 2's cancel. So frequency times length is equal to V. So length is equal to V over the frequency. So it's going to be 343 over 523, or 0.656 meters, or 65.6 centimeters. It's a little bit over 2 feet long. How about if we do one that's open-closed? So if I take a clarinet's open at the bottom and it's closed at the top where your lips are blowing in on the reed. So if I've got a clarinet that's 66 centimeters long, and we're going to say that it's a hot day, so the speed of sound is going to be 350 meters per second. Well, now what's the frequency of the lowest note on the clarinet and the next highest note? Okay, so since we've got an open-close, now I have to use those equations that have 4L. So I know my L is 66 centimeters, or 0.66 meters. Okay, so L is equal to 0.66 meters. And I know V is 350 meters per second. So what frequencies do I have? Well, I'm going to have 1. Frequency 1 is going to be 1 times V over 4L. And plugging that in, I get, excuse me, 133 hertz. You can see the details of the calculation there at the bottom. What's the next highest harmonic? Well, I can't have f equals 2. That's not allowed. I can only have odd ones. So I need to have n equals 3. So f3 is going to be 3v over 4l, which is just going to be 3 times 133, or 399 hertz. So again, remember, once you've found the frequency of the lowest harmonic, you can find the frequency of any other one just by multiplying the frequency of the lowest one by n. Okay, so now it's your turn to do some calculations. So let's do a calculation for a string for problem 1, where you're given the length of the string, the mass density, and the tension. And I ask you to find the wavelength and frequencies of the fundamental and the second harmonic. And then for a pipe, I want you to find the frequencies and wavelength for the 2 lowest harmonics if it's open at both ends or closed at both ends. Remember, that should be the same equation as each other. And then do one for when it's open at one end and closed at the other end.